So in this video, I'll then show you how to describe the span of a bunch of matrices. Again, the technique is exactly the same as you saw before with vectors. It just is more interesting because now you're dealing with an object that you don't feel quite as comfortable with. The ideas, though, are exactly the same. That's what's so powerful, is that the two ideas are fundamentally the same thing. All right, so then I want to describe the span of these three particular matrices. So then the span is just, well, by definition, it's just a set of all linear combinations. So I mean, that's the answer. It's just like, that's not very fun. It's right, but that's not really what we mean. That's just the definition. So I want to explain a little bit more. To do so, let's just pretend then that some matrix, in this case, it has to be a 2 by 2, would be in the span. And let's see if we can figure out some kind of relationship between all the entries in that matrix. So let's suppose then the matrix WXYZ is in the span. And let's see if there's some kind of dependency between W, X, Y, and Z. So if it is in the span, that means then there must be a linear combination of the three matrices that adds up to my matrix W, X, Y, Z. So then just like before, the left-hand side, you can condense down into a single matrix. The two matrices then have to equal. That gives you these equations all over again. But this time, the right-hand side, though, are unknown values, W, X, Y, and Z. That's okay. We're going to do the exact same thing I did before. That system there must be consistent because we're assuming that the matrix W, X, Y, Z is in the span. So there must be linear combination that adds up to it. So their scalars must exist. So C1, C2, and C3 must be numbers so that all those equations are true. So the system is consistent. So here's that system. Let's just write it down as an augmented matrix. Bang. And then we'll row reduce it. Now, when you row reduce it, though, don't row reduce the very last column. This is where you don't actually want to type this into a computer. You want to do this by hand. So looking only at the first three columns, you can row reduce it this much. Now, look at the very last equation. We know that the system must be consistent. In the last column, the first three entries in that first column are weird expressions in X, W, and Z in fractions. We don't care, though, because those are just numbers. The first equation would say C1 equals some number. Second row would then be C2 equals some number. And the third row is C3 equals some number. So actually, we don't care what those numbers look like. They could be any kind of crazy things. But if the system is consistent, that means the last row, that X minus Y has got to be 0. Because if X minus Y is not 0, there would have to be a leading entry then in the very last column, and that's not allowed. So since I know it's consistent, that forces that X minus Y has got to equal 0. Or in other words, X has to be Y. The minute we know that X has to be Y, that vastly restricts the type of matrices that can be in the span. So the only matrices that can be in the span are the matrices W, X, Y, Z, but remember, Y is X. So it can only be those matrices so that the entries on the main diagonal are equal. Do you remember the matrix I gave you before? It was 1, I think it was 1, 5, 5, 3. Did you notice that the entries on the off diagonal were equal to each other? That means that that matrix was actually in the span. While the other matrix I gave you was 1, 5, 4, 3. 5 and 4 were the off diagonals and they weren't equal. So then that matrix could not be in the span. So if I had known this ahead of time, I could have answered the first two questions incredibly quickly. Okay. Now, the next thing would then be is, since we have linear combinations and we've now discussed spanning, you can then talk about dependence, linearly dependent. The definition is exactly the same. All the consequences, in fact, are all the same. So then the basic definition is if you have a bunch of matrices, A1, A2, up to AK, we will say they are linearly dependent if and only if there is a linear combination of those matrices that adds up to the 0 matrix, where at least one of the scalars is not 0. If this is not possible, we then say that that set of matrices are linearly independent. So just have this nice correspondence if at least one of the scalars in the linear combination is non-zero, that means then the matrices A1 through AK are called linearly dependent. If they all must be zero, if you have a linear combination of these matrices that adds up to zero, and the only way that can be done is if all the scalars are zero, we call those matrices linearly independent. It's the exact same results we had before. And in fact, the way to go about figuring out if a bunch of matrices are linearly dependent or independent, it's exactly the same as before too. It's just a matter of just being careful. So I'll do this one by hand. So I want to know, can I verify for you that these matrices here are linearly independent? To do so, my answer would go like this. Let's suppose that there are scalars C1, C2, C3 exist, so that C1 times this matrix 1, 0, 0, 2 plus C2 times this matrix 0, 1, 0, 1 plus C3 times 2, 1, 0, 0, that equals the zero matrix, because that's what zero is here, zero matrix. So I'll show them that the scalars have to be zero, that the only way that's possible is if all the scalars are zero. If I could ever show that one of the scalars could be non-zero, that would then mean that these three matrices are linearly dependent. So exactly the same thing as before. I have a matrix equals a matrix, so the corresponding entries have to be equal. So on the left-hand side, just kind of multiply everything out, add it all up. So then you'd have a first entry be C1 plus 2C3. First row, second column, that would then be C2 plus C3. Second row, first column, that would then be the zero. That's just zero right away. That makes it easy. And the very last one, maybe second row, second column, that'd be 2 times C2. And then you'd have plus, 2 times C1. And then you'd have 1 times C2. So that's just C2. And that's equal to the matrix 0, 0, 0, 0. So that gives you the equations C1 plus 2C3 equals 0. That means C2 plus C3, that equals 0. And 2 times C1 plus C2, that equals 0. As an augmented matrix, that's 1, 0, 2, 0, 0, 1, 1, 0, and a 2, a 1, a 0, and a 0. But, and I'll just skip the work for you. If you just get the row reduced echelon form, you can use your calculator to do so. You'll get the matrix 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, which means that C1 is 0, C2 is 0, C3 is 0. So therefore, and I ran out of room. So at the end here, I would write, therefore, the three matrices are linearly independent, because the only linear combination of these matrices that adds up to the zero matrix happens to be the trivial one, where all the scalars are 0. Nice, right? I mean, it's very similar to what you saw before. There's really no magic here. It's just a matter of working in a slightly new world. So as a quick drill, let's just think it out. I want to describe the span of these two matrices. So think about what happens. The span would then be, it'd be some matrix of the form. It'd be a W, an X, a Y, and a Z, and it would be C1 times 3, 0, 0, 0 plus C2 times 0, 0, 0, 2. Well, if you just add the right-hand side, that would be 3 times C1, 0, 0, and you'd have 2 times C2. So think about it. C1 and C2 could be anything. So that means that W could actually be any real number. It means Z could be any real number, but X and Y can't be. X and Y have to both be 0, because again, corresponding entries have to be equal. So X must be 0, Y must be 0. So the span is the set of all matrices of the form W, 0, 0, Z, where W and Z could be anything you like. You also don't need to call W and Z. If you want to say A and B, totally fine. It doesn't matter. You're just calling those entries something. So in other words, the span of these two matrices is the set of all 2 by 2 scalar matrices. Remember, scalar matrices means that on the off diagonal, they're all 0. On diagonal, they can be anything you like. So then that is a generic scalar matrix. So the span of these two matrices is actually the set of all scalar matrices. Kind of neat, right? I think that's enough of that video.